Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 32, in which I will discuss on cosets. Let G with a given binary operation be a group H with same binary operation be subgroup of G. We may write elements of H as H equal to a set containing elements H1, H2, H3, identity element, this. Let A belongs to G. Then we write AH equal to here A operation H1, A operation H2, A operation H3, A operation E, means E is the identity element. So A operation E means A, this. In short, we may write AH equal to AH such that H belongs to capital H, subgroup of G. Then AH is called a left coset. AH is left coset. We write HA equal to, here we take operation A in right side, H1A, H2A, Here E operation A is A, and so on. And here we may write HA equal to H small ha such that small h belongs to capital H, subgroup. Then this HA is called right coset. When the operation is addition, then we write left coset as A plus H. A belongs to G. This equal to A plus small h. Small h belongs to capital H. This is the left coset. And for right coset, in the case of binary operation addition, we write H plus A equal to small h plus A. Small h belongs to capital H. Now we give some examples. Now we give the example. Let G be a group which is set of integers and binary operation is addition. H is subset of G and H is also a subgroup of G such that H equal to 3Z. with binary operation addition. We may write H as 3n such that n belongs to Z. Now, 0 element belong to G, 0 belongs to G, and 0 plus H equal to 0 plus 3n, n belongs to Z, and this equal to elements of the form 3n, n belongs to Z, and this is equal to H. Therefore, left coset 0 plus H equal to H. Since 1 belongs to G, since 1 is an integer that belongs to Z, that means 1 belongs to G, and 1 plus H equal to 1 plus 3n, n belongs to Z. This is another left coset. 2 belongs to G, and 2 plus H equal to 2 plus 3n, n belongs to Z. This is another left coset. Now we give another example. Let group G is S3, symmetric group of degree 3. That means permutation group of degree 3 in which binary operation is multiplication of permutations, that is composite mapping. Let H means a subgroup of S3 is rho 0, rho 3. Rho 0 be the identity permutation, and rho 3 is another permutation of 2 cycle. Here rho 0 H equal to rho 0 operation rho 0, rho 0 operation rho 3. This is rho 0 rho 3. This is identity permutation. So rho 0 rho 3 is rho 3, and this equal to H. Similarly, if we take rho 3H, here rho 3 rho 0, rho 3 rho 3, this equal to rho 3 rho 3 rho 0 means rho 3, and rho 3 square. Rho 3 is of 2 cycle, so we get identity permutation rho 0, and this is also H. So we get left coset rho 0 H equal to H, left coset rho 3 H equal to H. Now we prove a theorem. Let capital H be a subgroup of a group G, and small h belongs to capital H, then small h capital H equal to capital H. Since given that G be a group and H, capital H, be subgroup of G, and also given that small h belongs to capital H. Now we have to prove that small h capital H equal to capital H. That means left coset of capital H equal to capital H when small h belongs to capital H. Let P belongs to small h capital H implies that P equal to H1 for some H1 belongs to capital H. This is number 1. This is number 2. Since small h belongs to capital H, subgroup capital H, and H1 is also an element of capital H. Capital H is a subgroup implies that H1 belongs to capital H. This is number 3. From 2 and 3 we get P equal to H1 belongs to capital H. This is number 4. In 1 we see that P belongs to small h capital H implies that P belongs to capital H. That means small h capital H is subset of capital H. This is number 5. Let Q belongs to capital H and since H belongs to capital H, let this is number 6. Since Q belongs to capital H and given that small h belongs to capital H and capital H is a subgroup of G, that means capital H is a group, then we may get a unique element X belongs to group H such that Q equal to HX. Here X is unique element of capital H. This is number 7. Since small h belongs to capital H implies that small h belongs to G and here X belongs to capital H. Therefore HX belongs to H capital H. Left coset. This is number 8. From 7 and 8 we get Q equal to HX belongs to HH. That means from 6 and 9 capital H is the subset of small h capital H. This is number 10. From 5 and 10 we get small h capital H equal to capital H. Proved. Now we prove a theorem. Let capital H be a subgroup of a group G and small a belongs to G minus H. Then AH intersect H equal to phi. Now we prove this. Prove. Let G be a group with given binary operation and this H be a subgroup. This is H of G. Therefore, this part is G minus H. This part. Here A belongs to G minus H. A is an element of G minus H. We have to prove that A H left coset intersect H equal to phi. If possible, let P belongs to A H intersect H. This is number 1. Implies that P belongs to AH and P belongs to capital H. Here P is an element of AH. Therefore, P is of the form AH1 for some H1 belongs to capital H. Here P belongs to capital H. Therefore, P is an element of capital H. We may write P equal to H2. This is number 2. This is number 3. Therefore, from 2 and 3, we may write AH1 equal to H2. H1 is an element of capital H subgroup. Therefore, H1 inverse exists in capital H. Implies that H1 inverse equal to H2 H1 inverse. Implies that H1 inverse means identity element. This H2 H1 inverse implies that this is equal to A, identity element, and A becomes A, H2 H1 inverse. This is number 4. Since H2 and H1 inverse belong to subgroup H, implies that H2 H1 inverse belongs to H by closure property. This is number 5. From 4 and 5 we get A equal to H2 H1 inverse belongs to H, implies that A belongs to H. Here we see that A belongs to G minus H, but A does not belong to H. Here we get the result A belongs to H. Therefore, we get contradiction. Therefore, our assumption in 1 is wrong. In 1, we have assumed that AH intersect H contains an element, that is AH intersect H is non-empty. This concept is wrong. Therefore, AH intersect H is empty, that is equal to phi, null set. Proved. Now we prove a theorem. Let G be a group and H be a subgroup of G. Any two left coset of H in G are either identical or they have no common element. Let G be a group and H be a subgroup of G. A, B belong to G and AH, BH are two left cosets of subgroup H. If possible, let AH intersect BH is non-empty. That means there exists an element P belongs to AH intersect BH. Implies that P belongs to AH and P belongs to BH. We may write here P equal to AH1. P belongs to AH for some H1 belongs to H. Here P belongs to BH. We may write P equal to BH2 for some H2 belongs to H. Therefore, AH1 equal to BH2 implies that AH1 H1 inverse equal to BH2 H1 inverse implies that A, this means identity element, equal to B H2 H1 inverse implies that A identity element means A equal to B H2 H1 inverse. Let this is number 1, this is number 2. Again, since AH1 equal to BH2 here implies that AH1 we take H2 inverse equal to BH2 H2 inverse implies that AH1 H2 inverse equal to B, this identity element implies that AH1 H2 inverse equal to B implies that B equal to AH1 H2 inverse. This is number 3. Now let X belongs to AH. We may write this X equal to H3 for some H3 belongs to capital H. From 2 we get A equal to B H2 H1 inverse and here H3. Here H2, H1 inverse, H3 all are elements of capital H. Therefore, their operation will belong to capital H. So, here we get element B and element of capital H. This belong to BH. This is number 4 and this is number 5. In 4, X belongs to AH. Here in 5, X belongs to BH. That means AH is subset of BH. This is number 6. Again, let Y belongs to BH. We may write Y equal to B and some element H4 of capital H. For some H4 belong to capital H. We may put the value of B taking from 3. A, H1, H2 inverse, H4. Here H1, H2 inverse, H4 are elements of capital H, and capital H is a subgroup, that means group. Their operation will belong to capital H. So this equal to A and element of capital H. That means this belongs to A capital H. This is number 7 and this is number 8. From 7 and 8 we get Y belongs to BH, implies that Y belongs to AH. That means BH is subset of AH. This is 9. In 6, AH is the subset of BH, and in 9, BH is the subset of AH. Therefore, AH equal to BH. This is number 10. Therefore, we get that if AH intersect BH contains an element, that is, they contain a common element P, then two left cosets AH and BH are equal. And if they do not contain any common element, then they will be distinct left cosets. That is, their intersection is a null set, empty set, then they will be distinct left cosets. Now, I will give the details of my lecture notes. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.